Let's start with a quick revision of what we have covered already in this topic, rectilinear motion. So we are actually studying rectilinear motion in a chapter of kinematics of particles. So the motion is only in one direction by a given particle, and we started with actually three basic equations or relationships relating displacement, velocity and acceleration. So our equation 1 was V is equal to ds by dt, where s is the displacement, v is the velocity, and this can also be written as ds is equal to v dt, right? And it can also be written in integral form as ds integrated from some s naught to s value, where s naught is the starting value of displacement and s is at any time instant, is equal to integration from t equal to 0 to any value t v dt, right? So all these are the same forms of equation 1. We also studied the graphical interpretation of this equation, which says that the area enclosed by the velocity time relationship is graphically equal to, when you calculate that area, is equal to net displacement, right? So that was graphical interpretation. Area enclosed by v versus t relationship is net displacement. So if v versus t is given and you are asked to determine the net displacement from any t1 to any t2, graphically it will be this shaded area. So this will be net displacement between t1 and t2, right? The second equation we studied was equation 2, and that was A is equal to dv by dt. We can also write it as dv is equal to a dt, right? And also we can write it in integration form as dv from some value, starting value of v equal to v naught to any given v at a time t, is equal to integration of a dt, and the limits will be for t equal to 0 to t equal to some value t at a given time instant. So again, the graphical interpretation of this equation would be that the area enclosed by acceleration time relationship between any two time instants is equal to the change in velocity or net velocity of that particle. So same thing, if I have a versus t relationship, some equation, I can calculate the area between any t1 and t2, and this shaded area will be equal to the net velocity. The third equation was actually relating all three parameters, displacement, velocity and acceleration, and that was our equation 3. So equation 3 was, actually we combined 1 and 2 to get 3. It was v dv is equal to a ds. So v dv is equal to a ds was our equation 3, and this is actually determined using 1 and 2. It's relating all three, s, v and a, in one equation. And now we were actually at a stage where we were discussing different ways of applying these three equations to different types of problems, right? The first type of problem was that when we are already given with s versus t relationship, right? So let me just separate that part out, and now we will applying this three equations to different problems. So we already discussed and solved one problem of type 1. So let me call it problem type 1, in which s versus t was given, it was given, and you are required to determine v versus t and a versus t. Once you know these two relationships, you can always answer questions like what will be the velocity at that time, or what will be the acceleration corresponding to a given time, right? So all those questions can be answered once you have v versus t and a versus t. So this needs to be determined. So this is to determine. That was our first problem type, and the solution technique we discussed was successive differentiation. So once you already have a S versus T relationship, analytical relationship in the form of an equation, you differentiate it with respect to time to get V versus T. You differentiate it again with respect to time to get A versus T. And once you have these two relations, you can use them for answering any additional questions. But these two are your main unknowns, right? So that we already covered, and we saw one problem. So that was actually this case when S is given as a function of time. S is some f of t, for example this one, and you are asked to determine V as a function of time, A as a function of time. The next type of problem we started discussing was when A is given, acceleration is given, and then you are required to determine V versus time, S versus time. So back calculate velocity and displacement from acceleration. And in that kind of problem we saw that again there are 4 cases depending upon in which form acceleration is given, right? So that was actually the first case which we discussed already. We solved one problem. That was actually the second case. So generally acceleration is produced as a result of some applied force, right? And in this particular chapter we are simply given with that acceleration without reference to that force which produce it, and we will be required to determine V and S as function of time or any other function. So these were those 4 cases when acceleration is given. Acceleration can be given as a constant value, right? It can be given as a function of time. It can be also given as a function of velocity, and finally as a function of displacement, right? Out of these 4 cases, first 2 are very similar because our solution approach will be same for both of them, and that will be successive integration with respect to time, right? So I called this case as problem type 2, continuing the same problem types from previous topic. So problem type 2, then it can be a problem type 3, similarly problem type 4 and problem type 5. It will be very useful if you actually identify for any given problem, you identify what type it is, what is given, what is to be determined, and then immediately you should be able to get the solution approach or recall the approach to start the solution. First 2, as I have said, are very similar, and the solution approach is successive integration. Successive integration. So if acceleration is given a constant value, you integrate it with respect to time, you get a velocity time relationship. You integrate it one more time, you get a displacement time relationship, right? Same is the case when acceleration is given as a function of time. So since the function is already in time, you can integrate it with respect to time, one time to get velocity versus time. You can integrate it one more time to get displacement versus time, right? So first 2 are kind of simple cases. We already covered the first 2 cases. First was constant acceleration case, and then second was when acceleration was given as a function of time. So we will be mainly discussing the case C and D today, and then we'll see a couple of problems related to those cases. In constant acceleration case, we derive this expression. Since acceleration is given as a constant quantity, so when we apply equation 2, we can take A out of the integration, and therefore were able to derive this expression which is simply relating velocity as a function of time, right? So A is a constant quantity here in this equation. When we apply equation 1 or kind of integrate this function with respect to time, again we will get displacement, and that displacement was this function. Again we were able to derive a closed form formula because acceleration is constant, so we were able to carry out that integration. One more thing which we can derive in the same case, let's discuss that and then move to the other cases. That was, see, we actually applied equation 2 and equation 1 here. If we apply the third equation, equation 3, which was actually V dV is equal to A ds, if we apply to this constant acceleration case, in integration form it will become V naught to V and integration of some S naught to S. If acceleration is constant, we will be getting A out of the integration, and then we will be having S with a limit S naught to S on right hand side. But on left hand side we will be having V square over 2 with a limit V naught to V. So this will give us another relationship for constant acceleration case, and you will also be applying that in different problems. So for example, that relationship will become V square by 2 minus V naught square by 2 is equal to AS, right? Or in other words, I can say V square is equal to V naught square plus 2A. Actually it should be not S, when I apply the limit it should be S minus S naught. For all the cases where the motion start from time t equal to 0, then we will be having S naught as 0, otherwise it was S minus S naught. So that relation is actually relating again the all three quantities similar to equation 3, which was V dV is equal to ADS, but we write it in another form relating acceleration, velocity and displacement all in one equation, right? But again all three equations, this one and the last one, they are all applicable to constant acceleration cases, right? The second case was the case when acceleration is given as a function of time, and the solution technique was same. We have to integrate it 2 times to convert into velocity and displacement. But in this case, you know that we don't know what function it is. It will be given from problem to problem different function. So therefore we are not able to derive a closed form expression. All we can do is that we apply equation 2, and whatever that function is, we integrate it from 0 to t and then calculate velocity as a function of time, and then again introduce that velocity in equation 1 to integrate it one more time with respect to time and get displacement, right? So finally we will be able to get displacement as a function of time and also velocity during that process. So in a way the solution technique for both case A and B are similar, but the difference is that for case B you have to actually evaluate that integral which is given to you. Now let's continue to case C, where acceleration is given as a function of velocity. One more thing before going to that is about case B, and that is, although we can approach the problems using this solution approach, but there can be an alternate idea also. An alternate approach would be, which we might not be going into detail in this course. So alternate approach can be that, for example, you have A as the second derivative of S, so S double dot, that will actually can also be written as d2s by dt, right? Now A is expressed as a function of time, right, in this case. So we can also make a second order differential equation, and that will actually become S double dot is equal to f of t, the given function which is actually A, right? And then it will be S double dot minus f of t is equal to 0, right? This can also be written as, for example, d2s over dt square minus f of t is equal to 0, right? So this bottom equation which I am encircling now is a second order differential equation, right? Relating S and T. If you are able to solve that equation, you also will be able to get S versus T relationship, the relationship which you have derived here, right, for that particular function. So that is an alternate approach by converting the problem into a differential equation. So just like you can solve algebraic equations and there are specific solution methods for second degree polynomial, third degree polynomial, similarly in differential equations you will have different solution approaches for first degree ordinary differential equation, second degree, third degree and all higher degree equations. Now let's move to case C when acceleration is expressed as a function of velocity. We will be starting with applying equation 2 first. Equation 2 is A is equal to dV by dt, or in other words dV is equal to A dt, right? Now since acceleration is given to you as a function of velocity, so let's take acceleration on the other side and write it as 1 over A dV is equal to dt, right? Acceleration is given to you as a function of velocity, so we are moving velocity terms on one side. In integral form it will become v naught to v with respect to v, and from t equal to 0 to some time t, right? Now A is expressed as a function of velocity. For example, you will be given with A is equal to minus 3 v square, right? Now this is an example of how acceleration can be expressed or given as a function of velocity. So you will be introducing that function, so it will become 1 over f of v, v naught to v dv is equal to t, right? When you apply limit from 0 to t it will become t, right? So t will be equal to this integration which you can solve analytically because everything is now function of v in that, right? So you can carry out this integration on the right hand side as a function with respect to velocity actually, and get a relationship between time and velocity, right? So when you evaluate that integral, apply limits, you will be getting v versus t relationship, right? V versus t relationship. And then what should be the next step? Once the velocity can be expressed as a function of time, you can integrate it one more time to get displacement, right? So the next step should be applying equation 1, which is v is equal to ds by dt, right? And in other words ds is equal to v dt, right? So let's write it the same equation in integral form. It will become ds v dt, and it will be from s naught to s, from 0 to t, right? Now v you have already determined as a function of time, so please put that in this integral and integrate it one more time as a function of time. So this will become s minus s naught is equal to this integration, which we cannot solve because it depends on the function which is given to you in that problem, and s can be expressed as s naught plus 0 to t v dt, right? So this will be your final relationship which is relating s and t, or s is being expressed as a function of time, right? This case C also have an alternate solution approach, and that is using equation 3, right? Alternatively, you can also carry out the same thing by applying equation 3, and equation 3 is v dv is equal to a ds. Now you know that acceleration is given to you as a function of velocity, so you can take acceleration here on the other side of the equation. It will become v over a dv is equal to ds, right? And in integration form it will become from v naught to v, and this will become s naught to s, right? So now a is expressed as a function of velocity, so you can put that function here and left hand side of this integration will be all in terms of velocity, right? And you can analytically solve that integral depending upon what function is given to you, and then when you solve that integral it will become v over fv dv from v naught to v, and on the right side, if I go back, on the right hand side you will be simply having s minus s naught, and s can be finally expressed as s naught plus this integral v over v naught to v over f of v dv, right? So we move to the final case, a is equal to f of s, which means acceleration is expressed as a function of displacement now, right? This will be a relatively complex case compared to the first three cases. The solution technique actually starts with applying equation 3, and equation 3 is v dv is equal to a ds, right? Now acceleration is already given to you as a function of s. So if you put that function here, it will become f of s ds is equal to v dv, right? And in the integration form it will become from v naught to v and s naught to s, right? Again, now right hand side is all in s variable and left hand side is all in v variable, right? Right hand side we cannot evaluate until we are given with that function a related to s, but left hand side we can solve. It will become v square by 2, and when the limit is applied v naught to v, this will be same thing. When I apply the limit, it will simply become v square over 2 minus v naught square over 2 is equal to the same integration s naught to s f of s ds, right? Then it will become v square is equal to v naught square plus 2 times integration, same integration, f of s ds. So this last equation is actually, that one is actually relating velocity with distance, right? But when you evaluate it, put that limits and everything, you should be getting velocity as some function of s. So let's call that function which you will be solving using this integral, let's call it some g of s to differentiate it with f of s, right? So velocity in terms of s can be determined using this equation, but our solution won't be complete unless we get distance or displacement versus time relationship. So we will be applying equation 1 now, which is v is equal to ds over dt, or in other words ds is equal to v dt, and we can also take v here, so it will become 1 over v ds is equal to dt. In integration form it will become s naught to s and 0 to t. Now v is already determined in last case here at the bottom as a function of distance, right? So we can put that function here in this equation instead of v, so we can write s naught to s 1 over that function g of s ds is equal to t here, and limit will be from 0 to t, right? This should finally give you t as equal to this integration s naught to s 1 over g of s ds, right? You should be able to evaluate the right hand side of this equation at the bottom because everything is now in s, right? So integration with respect to s can be carried out, and finally this equation should give you the displacement versus time relationship, right? So that will be your ultimate goal or output from this whole exercise, right? Once you calculate s versus t analytically, you can take its derivative with respect to time one more time to get v versus t, right? So case 4 is actually applying the same equations, equation 3 and equation 1, but in a bit different form, right? So I repeat again this case. We started with equation 3 and we determined a relationship between V and S. We call that as some G of S. And then we apply equation 1. So this is our equation 1. And we put V as a function of S in here and integrate with respect to S to finally calculate the displacement versus time relationship, analytical relationship, right? So now we actually covered 5 different problem types. First, when S versus T was given and you need to differentiate it to determine V and A. And the next 4 are when A is given and you need to integrate with respect to time to calculate velocity and displacement. But again, you can see that the way you integrate acceleration in these 4 cases is different, right? For first 2 cases, direct successive integration was possible, but for the last 2 cases, case C and case D, you need to integrate it in slightly different form to convert one variable to other and then come back to the third variable, right? So the problems you will be seeing in this particular part of this chapter will require you to integrate different functions, right, depending upon how acceleration is given. In most of the cases, the function given to you, for example, A as some f of t, or A as some f of v, or A as some f of s, there will be simpler functions which you can integrate analytically using basic calculus knowledge, right? So analytical integration will be possible for many of these cases which you will be dealing with in dynamics, right? But there can be certain real physical scenarios or cases where the actual function relating A and velocity, A and distance, for example, may be very complex, right? And the analytical integration or simple methods of integration may not work in those cases. So you may be going to graphical integration in those cases, and you can also opt for numerical integration. Numerical integration is an approximate integration method in which you divide your integration problem into small segments and then approximately determine each segment and then sum to get the same integration numerically. And then there can be several computer aided integration methods also. So maybe one method can be like using computer aided integration methods, but mostly we will be dealing with the first case where the functions relating time, velocity and distance and acceleration, they will be simple enough to be analytically integrated, right? There are several methods in numerical integration, and numerical integration is mostly suited for those cases where you don't have an analytical equation or relationship between acceleration and any of these quantities. When the data is also, or given input is also numerically defined, and now you need to integrate that function, then you should use numerical integration. Imagine that I give you, for example, instead of giving you an equation between A and T, I say that A and T is like this, that at one value I give you a value, for second, third, fourth I give you like discrete values, right? So you can join them to make a graph between A and T, but you may not be given with an equation directly. So maybe I can give you, imagine a case where you are given with time versus acceleration data at 0, 1, 2, 3 seconds and the acceleration value is given, right? In all such cases where the function is not available and you are given a numerical data relating to variables and now you need to integrate that function, you will actually opt for numerical integration methods, but not in this course. Here the functions will be simple enough to be analytically integrated.